So for Poisson distribution, it's pretty much binomial distribution where n is set to be infinity. So pretty much n try I'm success is binomial, and for Poisson is you have n equals infinity tries, and how many times you will success will be successful. So pretty much we're just going to take the limit of the binomial distribution and just plug in the combination formulas. We have this, and since we define the variable lambda is np, then pretty much we can substitute p equals lambda over n. Substitute here and here. We got this. So we just expand pretty much this two terms to this n multiplied by n minus 1, so on and so forth, to n minus m plus 1. So pretty much this is this. And here is here, m minus 1, and this is lambda here, and m to the factorial here. And this pretty much can be to the nth power divided by to the mth power. This will become apparent after a bit. Since we know for the limit of n to the infinity 1 minus lambda over n, this is like classic real analysis limit. It's e to the negative lambda. So this become e to the negative lambda, and this is since this is extremely small and this is a finite number, then it is 1. And for a limit of infinity and m is a finite number, then if they have the same terms, then thus it's pretty much become like this, and this is all really close to 1. So this is 1. So this thing equals 1. This thing equals 1, and this thing is finite, and this thing is e to the negative lambda. If you plug everything in, this is 1, this is 1, and this is e to the negative lambda. Then we have the distribution function right here, and the lambda is np. To calculate the expectation value is similar to binomial to degree. So here is I e to the m, I summing from 1 to infinity, and this is distribution function. Since the first zeroth term is 0, you can just start summing from 1 and take the lambda out, and I over I factorial is I minus 1 factorial. So we got this lambda taken out. So we have this become lambda multiplied by lambda I minus 1. And we have this and this become I minus 1 factorial. Exponential stays the same. If we set j equals I minus 1, pretty much is I substitute I with j plus 1 here and here and here, we have essentially j plus 1 minus 1, and j plus 1 minus 1. We have this, and this. Lambda is out. This looks familiar. It's pretty much, I'm sorry. This is pretty much the sum of the probability. A sum of probability distribution is 1. Thus, just left with the front term, lambda. Therefore, the expectation value is lambda. And let's try to calculate using similar principle to calculate e to the m squared. So again, I square distribution. Since the zeros term is 0, we can start calculating from 1. Taking a lambda out. We got this. And we have I squared become I, and multiply I divided by I on both sides. This I factorial become I minus 1 factorial. And substitute j equal to I minus 1. So I equals j plus 1 here, here, and here. This thing looks familiar. Again, let's not get there yet, but you can divide it into two things. One is this, another is this. This is the expectation value. This is probability. Then we have lambda multiplied by expectation value lambda multiplied by lambda by 1. This is the sum of all the probability. Thus we have e to the m squared equals lambda plus lambda squared. And variant is pretty much expectation value of m squared minus expectation squared. And we get lambda. Thus, the distribution is that, and the variant and the expectation value both are lambda equals NP.